So, my name is Brandon Allen, and I like to talk a lot, and so I'm going to try to refrain from talking a whole lot, but still getting the time constraint. So, what I did for my presentation is something on chromatic numbers. Now, when I went to Bemidji State up north, which is different than Winona State here, right, I took a course called Discrete Mathematics, which dealt with a lot of real-life problems that you see with mathematics and applying for students who do not really have the calculus background. But it still goes really technical because what I did in discrete mathematics directly relates to a thing called graph theory, and graph theory relates to having vertexes, right, points on a domain and connected by an edge to another vertex point, and so it creates a graph. So chromatic numbers deals with graph theory, and we'll see why here, but chromatic numbers will go over the relevant problems with chromatic numbers, what a chromatic number is really, chromatic and non-chromatic graphs. So there's a difference, right? There are properties and the cycles of chromatic graphs, and there's maximum chromatic numbers, and there are applications to chromatic numbers, like I've stated previously before. There are relevant problems with chromatic numbers that we see in business, in chemical engineering, with traveling, with scheduling, and coloring of maps. So we want to reduce chemical biohazards because if we have a truck traveling, it's carrying all these dangerous chemicals, and we don't want any of the chemicals to react and combust the truck, by killing the truck driver and saving a lot of money and value that way. We don't want things to combust and happen. So chromatic graphs are really helpful with that. We also want them to help us schedule shifts where people are in different committees, and this is very useful in the Senate, where they're on many committees and they don't have the time to allocate for all of them, or getting them at the smallest number of meetings as possible. And then these coloring graphs, if you heard the four color theory, this directly relates to chromatic numbers. And so I should actually get to what a chromatic number is. So basically, when you color a graph, right, when you have two vertex points, right, as seen here, we have one that's red and one that's green, and they're both different colors. And so each vertex is assigned to different colors. We don't have one that's red and the other one that's red, or one that's green and the other one that's green, because then it's not chromatic by definition. And so when a graph is colored with n colors, but not with a smaller number of colors, it's said to have a chromatic number n. So this definition of coloring graph is directly related to chromatic number, in which we have these two properties, such that we want the smallest number of colors, right? And so we're going to go on to what's chromatic versus non-chromatic in my eyes. And so chromatic, right, you see the triangle here as connected edges, such that none of these, right, are matching. But this can be red, because this point isn't connected with any of the others. And so this point here, red, can go along with the other red point. Whereas this would be non-chromatic, because I can simplify my graph to have 3 colors, right, instead of 4 colors, right? You want to reduce the amount of supplies that you use. Example, if these were the number of trucks that I can use with chemicals that I need to travel, right, I would rather want 3 trucks rather than 4 trucks, because that would save me money. Okay, remember, when a graph is colored with n colors but not smaller a number of colors, it's said to have a chromatic number n. Okay, now these are properties of cycles. Now you see here on the first one on the left that it has 6 vertices, right? It has an even number of vertices on them. And on the right one, it has an odd number of vertices. And what we have then is that we can color them, and so that even cycles, right, always have this definition where the chromatic number always equals 2. You can always separate it out by an alternating color scheme in a cycle. And if the odd cycle, it's always when n is greater than 3, greater than or equal to 3. So, right, we can travel along, but if I did two colors such as red, blue, red, blue, red, well, that's a contradiction. You can't have that. And so that's why odd cycles always have to have n greater than or equal to 3 number, chromatic number. And so you say to yourself, okay, how about if I have like a really complex networking graph that I was going to include in my presentation here? What if I had a really complex network graph that had billions of points, right? And you're like, how in the world do I know that number of colors, right? I don't know that number of colors. So, right, mathematicians have proved that you can simplify this to be the maximum chromatic number scheme, in which basically you have a vertex, and each degree of that vertex is the corresponding edge to this vertex. That's why it's saying the maximum chromatic number, the number of graph G, cannot extend one more than the maximum of degrees of vertices, right? So it can have a chromatic number of 5, right? Because you have 4 edges, right? And one more would be 5, but, right, you can just color it with 2. Okay, and an application of this would be dealing with the United States of America, right? Where we have the map of the United States of America, we take a portion of it, right? And we separate the states by their boundaries, right? The boundaries constitute those edges that we have, those defining characteristics between one vertex versus another vertex. And when we have this, right, we have that some points, right, can't go as the same color as others, right? And we see that here, as we're going to get the least number of colors possible. Now, it's been proven that the US can be colored in 4 colors, in which I'll show shortly. But right here, we see the chromatic number here is 3, due to what I've selected as my portion size of the United States of America. Okay, and so here's the United States of America. The lakes are colored in blue here, and the states, right, are colored so that each boundary, right, has a different color. And this is very useful for people who want to print things out and reduce the amount of color that they use for their business, right? You want to save money, as I say. And so when we do this, the reason why we have 4 colors is this area right here, with Colorado, Utah, Wyoming, Colorado, Utah, Nevada, Arizona, New Mexico over here, in which you'll have a space in which it's impossible to color with 3. And so you're going to have to color it with 4. And this was proven by Apple and Hannikin in about 2002, so very recently. It's been a troubling thing for mathematicians, but what they did was computer-run simulation systems, right? And basically the 4-color number theorem says that, chromatic number theorem says that you can color pretty much any vertex diagram, right, in just only 4 colors. Okay, and so now I'm going to move on to another application which deals with biochemical hazards, right? Well, I described, you know, you have a truck and each one of these vertices resemble a chemical, and if I hit, right, into a chemical that's dangerous or could make it explode, kind of like if you have the alkali metals, such as lithium with chlorine, for example, it makes it combust, right? And you don't want combustions to happen inside your truck. And so basically, we say to ourselves, well, how many trucks will it have to take for us to get that travel, or how many packages will we have to take to get across safely to another location? So we see that there's 3 trucks, right, when I color the vertex. And so with that, there are many applications that you can do with chromatic numbers, and future research that I see is the probability of different combinations in which you can shift chromatic number packaging with real world items. Any questions? Thanks.